Welcome to Nova Sleep. The night is still, yet something beneath it hums. A quiet vibration threading through every atom in existence. Across the universe, particles move in perfect harmony, mirroring each other's choices from impossible distances. No light, no signal, no sound, only connection. Physicists call it quantum entanglement, a mystery so profound it bends our ideas of space, time, and reality itself. Tonight, as you drift towards sleep, we'll follow those invisible threads beyond the limits of light, into the secret network that binds the cosmos together, and perhaps you to everything that has ever been. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you're watching from and what time it is, I would love to read it in the comments. 1. The universe hides invisible threads that link distant particles. Entanglement begins as a mathematical bond inside a single wave function, yet experiments keep showing that the bond acts like a real connection. Two quanta created together emerge with properties that cannot be assigned independently, as if each one finishes the other's sentence. The separation in space does not weaken the link, since the description of the pair lives in a joint state rather than two separate stories. What looks like two objects in three-dimensional space is often better described as one object living in a larger space of possibilities. The strange part is not mere correlation, but the way those correlations defy any explanation based on shared instructions written in advance. Classical common causes can mimic some patterns, though never the full pattern seen in modern tests. The observed statistics carry signatures that no hidden checklist can reproduce, which is why the field speaks about non-locality without signaling. The threads are invisible because they are not tiny wires in space, they are rules about what outcomes can appear together. When entangled partners are measured, the pair behaves like a single dice roll split across distance. The sum of certain outcomes becomes fixed even though each outcome alone looks random, and that fixed relationship persists no matter how far the dice are separated before the roll. The mathematics packages those constraints into a joint amplitude that interferes with itself, shaping what can and cannot happen. The interference lives in an abstract space, yet it leaves a footprint that detectors can count. The deepest insight is that the world does not always divide cleanly into parts. The whole can carry information that none of the parts hold alone, a feature called holism in physics rather than philosophy. In that sense, the hidden threads are not additives placed between particles, they are the failure of separability as a universal rule. Where everyday intuition says 2, quantum structure often replies 1, 2. Einstein's spooky action keeps defying common sense. The phrase spooky action was a protest, a reminder that a good theory should not rely on magic tricks. The complaint targeted the way measurement on one particle seems to decide the fate of another, far away without any physical messenger. Decades later, the shock has not faded, because the statistics keep confirming that the effect is real and not an artifact of faulty apparatus. Experiments that once looked like curiosities have matured into technologies. The stubbornness of the effect forces a choice among world pictures. Either influences outrun light in some hidden way, or measurements do not simply reveal pre-existing properties, or reality has branches that never meet, or some mix of these ideas holds. None of those options looks comfortable through the lens of daily experience. Common sense evolved for some stones and storms, rather than photons and spins. Modern optics lets laboratories push the riddle into new settings. Entangled photons are created and separated by city scales, then measured under conditions that prevent any last-moment coordination through ordinary signals. The correlations persist with a reliability that designers of communication networks would envy, and yet no usable message has ever been extracted from the instant link. The world allows spooky order while still guarding the speed limit for information. The phrase spooky action suggests a ghostly force, yet the better interpretation removes force from the story. The effect arises because the pair belongs to one quantum state, so talk of action from one site to another can be misleading. The weirdness is baked into the structure of possible outcomes rather than transmitted afterward. Common sense bends because the underlying book of rules turns out to be different from the book used in daily life. 3. Bell tests rule out local hidden variables with stubborn clarity. The logic behind Bell tests is a tight net cast over all classical explanations that use shared instructions. If particles carried a set of secret tags telling them how to respond to every setting, then certain combinations of measured correlations could never exceed a fixed bound. The surprise is that nature routinely breaks those bounds, not by a hair but by a margin predicted by quantum theory. The breaking is repeatable and grows cleaner as detectors improve. Early experiments left room for loopholes, which critics used to argue that maybe the tags were not sampled fairly, or maybe too many events were missed. Step by step, those gaps were closed through better sources, faster electronics, and careful scheduling. Modern tests choose settings at the last possible moment, capture nearly all pairs, and isolate the stations so tightly that no ordinary signals can sneak between them in time. The violations survive under these harsher conditions. The conclusion is not that cause and effect are dead, but that local realism as packaged in classical models does not describe the world. Either locality fails in a subtle sense, or realism about pre-existing values needs revision, or both. The tests do not force a single interpretation, yet they fence off large regions of the classical map. What remains shares a core feature: the joint system carries facts not owned by either particle alone. Bell's program also changed the attitude of the field. What once looked like a philosophical puzzle became a tool for engineering secure keys, certifying randomness, and benchmarking quantum devices. Correlation is no longer just a curiosity, it is a resource measured in bits and converted into performance. The stubborn clarity of those inequalities turned metaphysical debates into practical checklists. For CHS inequalities and the strange number called the Surelson bound. A convenient form of Bell's idea uses 2 settings at each station and 2 outcomes for each measurement. From those 4 options, one builds a score that classical models can never push past a value of 2. Quantum mechanics can drive the score higher, yet even quantum mechanics hits a ceiling at 2 times the square root of 2, a limit named after a mathematician who computed the maximum. The presence of a ceiling is as telling as the violation itself. That special number marks the edge of what the theory allows while keeping the rest of physics intact. Push the score beyond that bound and other cherished rules begin to break, including the rule that messages cannot travel faster than light. Nature sits at a sweet spot, more non-classical than any pre-quantum model, yet not so wild as to unleash supercommunication. The boundary sketches the shape of the possible. The bound also shows up in unexpected places. It connects to geometry through vectors on a sphere, to information theory through constraints on data processing, and to computer science through hardness results for certain games. This web of links suggests that quantum theory is not an arbitrary set of tricks, but the unique solution to a deep optimization problem. The strange number acts like a signature that appears on many pages. Practical labs now match the predicted quantum score within tight error bars. The match is not only a victory for textbooks, it is a calibration for devices that hope to use entanglement as a fuel. Reach the bound and one knows the setup is close to ideal. Fall short and there is room to search for loss, noise, or imperfect alignment. 5. Entanglement does not send messages, yet correlations arrive without delay. The instant pattern in measurement outcomes tempts the imagination toward faster than light chatter. That temptation fails because the local outcome still looks perfectly random, so no sender can impose a pattern that a receiver could read in isolation. Only after comparing long lists did the hidden regularities show, and sharing those lists requires ordinary signals that respect the speed limit. The world pairs immediacy with confidentiality. The distinction between correlation and communication protects relativity while preserving quantum strangeness. A joint state can encode rich structure that no single side can unlock alone, which explains why attempts to mine the link for messages always end in noise. The lesson is subtle yet firm. Nature allows stronger together than separate, yet refuses to turn together into a telegraph. Security professionals recognize the opportunity immediately. The no messaging rule does not make the phenomenon trivial. Instant structure matters whenever 2 labs want to certify that their data agrees beyond classical explanation, without trusting each other or the hardware. The pattern provides a stamp of authenticity that counterfeiters cannot forge with local tricks. In that sense, the correlations behave like signatures issued by the laws of physics. This pairing of power and restraint also hints at a deeper architecture. Perhaps space-time and information are intertwined so that non-local structure can live safely on top of causal order. Theories that see geometry emerging from entanglement lean on this complementarity, a dance between what is linked and what can be used. The dance looks paradoxical only when everyday language tries to compress 2 rules into one sentence. 6. Two photons that share one wave function behave like one object. A typical source produces photon pairs whose polarizations are not fixed in advance, but tied together in a balanced superposition. Rotate one polarizer and the pattern of coincidences rotates in a connected way, which is why the pair must be treated as a single state. The mathematics never splits into a product of two parts, a sign that neither photon owns a definite polarization until the joint measurement project is complete. Togetherness is not a metaphor, it is the algebra of the state. The one-object picture shows its strength when the pair faces interference tasks. Effects that require two paths for one particle can be executed by one path for each of two particles, provided the paths meet in the right way. This trick underlies entanglement swapping and teleportation, where clever beam splitters and detectors trade partners and move states without moving energy. The laboratory diagram looks like plumbing, the underlying process reads like logic. Photon pairs also highlight fragility. Tiny amounts of loss or stray noise reduce visibility in the interference fringes, which reduces the certifiable strength of the non-classical link. Engineers fight back with better crystals, brighter sources, and careful filtering that preserve coherence while maintaining count rates. Each gain makes field tests over larger distances and rougher channels possible. The same hardware that proves principles begins to look like infrastructure. Fiber corridors carry entangled light between city nodes and free space links, bridge islands, and satellites. As stability improves, the joint wave function becomes not only an idea but a commodity that can be generated, routed, and consumed. The one object becomes a service. 7. Loophole-free experiments close the last classic escape routes. Early data could be explained away by arguing that too many pairs were lost, or that settings were chosen too slowly to defeat last-second coordination. Modern experiments confronted those points one by one, boosting detector efficiencies, creating brighter entangled sources, and using fast random choices made during each run. The result is a class of tests in which no simple classical explanation survives the careful audit. The phrase loophole-free marks a milestone rather than an end. Achieving these conditions requires a choreography that spans chips, lasers, and timing electronics. Separate stations must be far enough apart that light cannot carry a message between them during a single trial, yet close enough that a stable source feeds both with minimal drift. Random choices must be produced quickly and applied cleanly, so that the measurement bases do not leak or bias the data. The raw counts then pass statistical tests that account for finite samples and memory. The effect of closing loopholes is not merely psychological. Security protocols can claim stronger guarantees when the data comes from such configurations, because the design blocks hidden side channels that an adversary might exploit. Device-independent methods demand exactly this level of careful construction. Practical cryptography borrows integrity from fundamental physics. The path forward now points towards scale. Instead of two stations and two settings, networks will involve many nodes, adaptive choices, and error correction. Each added layer presents fresh places where loopholes could reopen, so the discipline born in two-party tests must carry into web-sized deployments. The lessons of the cleanest experiments become the hygiene of a new technology. 8. Satellites distribute entanglement across hundreds of kilometers. Ground-based fibers suffer loss that grows exponentially with distance, which strangles entanglement long before continents can be bridged. Placing a source above the atmosphere cuts scattering and absorption, letting delicate photon pairs travel farther with fewer interruptions. Demonstrations now show entanglement shared between space and ground, with key generation and teleportation trials that span countries. The sky turns into a relay for quantum links. These missions solve problems that look mundane yet decide success. Pointing accuracy must hold within tiny angles while platforms move at orbital speeds, and thermal changes can tilt optics or shift frequencies unless stabilized. Detectors need high efficiency and low noise despite the flood of background light from Earth and Sun. Each subsystem wins a battle so the whole chain can pass a photon to the right place at the right time. Results from these flights validate the dream of a global quantum network. Cities far apart can share correlated light generated on a passing satellite, then build secure keys that no eavesdropper can reconstruct from intercepted fragments. Follow-on designs will mix space and fiber, using repeaters on the ground and trusted or trustless nodes in orbit. The network grows together from above and below. The motivation is not only communication. Satellite platforms provide a clean stage for tests of fundamental physics in regimes hard to reach on Earth. where gravitational potential varies along the path and long baselines are cheap. Entanglement becomes both a tool and a probe, sensitive to tiny effects that might whisper about new principles. Space turns into a laboratory sized like a planet. 9. Cosmic tests use ancient starlight to pick detector settings. A lingering doubt in early work was that random choices used to set measurement directions might hide subtle correlations with the source. The fix was audacious. Let the universe make the choices by using light from distant quasars or stars as switching signals. The time between emission and detection spans billions of years, which fences off any mundane coordination scheme. If conspiracy remains, it must be written into the cosmos at a scale that drains the doubt of meaning. In practice, the setup sends the intensity or colour of incoming cosmic light into electronics that flip polarizers or choose angles in the moment before each detection. The distances between stations preserve locality, while the origin of the settings vaults past any shared past with the entanglement source. The resulting violation of Bell bounds looks the same as in laboratory-generated randomness, only now the choices carry an ancient pedigree. The stars become coin tosses. These experiments add poetry as well as rigour. The photons that set the switches began their journey when the solar system was dust, yet arrive in time to confirm that non-local correlations are not a trick of nearby causes. The method ties together cosmology and quantum foundations in a single instrument. The night sky signs the data. Work continues to push the selection further back and to reduce any contamination from local noise. Each improvement squeezes the small remaining space where classical accounts might hide. The crosstalk between astronomy and quantum information deepens as both fields supply tools and motivations to the other. Old light answers new questions. 10. Superdeterminism asks whether freedom of choice is only a story. One escape from Bell's net proposes that choices are never truly free, that hidden variables conspire with future settings, so the data only looks non-local. If everything, including the experimenters and their random number generators, is tied together by deep initial conditions, then ordinary reasoning about independence fails. The idea cannot be dismissed by logic alone, since physics already treats the universe as one evolving whole. The difficulty is to make the proposal testable. A useful version would produce new quantitative predictions that differ from standard quantum theory in ways a laboratory can probe. Attempts along these lines explore how correlations between settings and hidden variables might subtly alter the distribution of results, though, without breaking successful quantum recipes elsewhere. Building such models has proven hard, because they must preserve the accuracy of a vast range of experiments while changing the foundation only in precise places. The bar sits high by design. Critics argue that the cure costs more than the disease. Giving up statistical independence undermines the very method by which science isolates causes, since any outcome could be blamed on conspiracies seeded in the past. Supporters reply that discomfort is not a refutation, and that nature might be deterministic in a way that masks itself at human scales. The debate sharpens the understanding of what the usual assumptions really buy. Regardless of the verdict, the topic clarifies the power of modern tests. The reach of cosmic setting choices, the speed of random generators, and the physical separation of stations were all motivated by the wish to defend independence as an empirical stance. If superdeterminism ever offers distinct numbers, those same tools will be ready to check them. Until then, the simplest reading remains that freedom of choice is good enough for work. 11. Entanglement swapping binds two particles that never met. Ordinarily, entanglement seems to require a shared birth event. Two photons emitted together from a common source, or two atoms interacting directly. Entanglement swapping overturns that assumption by proving that a clever sequence of joint measurements can fuse separate pairs into a new link between strangers. In a simple setup, photons A-B and C-D each begin entangled within their own pair. A joint measurement on B and C erases their individual identities and projects A and D into an entangled state even though they never crossed paths or shared any physical contact. The power of the procedure lies in how information rather than energy connects the chain. The act of measuring B and C in a special entangled basis forces their distant partners to collapse into complementary outcomes, effectively knitting the outer ends of two fabrics into one continuous weave. Quantum theory predicts this with unerring precision, and experiments confirm it again and again. The key is that the intermediate particles serve as translators between separate entanglement links, forming a bridge that requires no material thread. Entanglement swapping is more than a trick of quantum algebra. It is the heart of large-scale quantum networking. Without it, each link would die after a few kilometers, doomed by a loss and decoherence. With it, quantum repeaters can stitch together a chain of short-lived segments into a continent-spanning connection. The swapping measurement acts like a handshake that passes coherence along a line of participants, extending the reach of non-local correlations beyond any single laboratory. Even philosophically, the concept unsettles ordinary intuitions about cause and sequence. The final relationship between A and D seems to depend on a measurement that happened in the middle, sometimes even after A and D were already detected in delayed choice versions. The idea that two entities can be deeply related without ever sharing a meeting point hints that reality's fabric is woven from information rather than proximity. 12. Delayed choice experiments reshape history after the fact. At first glance, it appears impossible for a future measurement to rewrite what a particle did earlier. Yet delayed choice setups force that very reconsideration. In these experiments, light passes through an interferometer that can either recombine its paths or leave them separate. The choice to recombine, deciding whether the photon behaved like a wave, can be made after the photon has already entered the device. Results show that the outcome aligns with the later decision, as if history waits for a verdict before solidifying. The mathematics does not literally send influences backward in time. Instead, it withholds final meaning until the entire experimental context is known. Quantum systems evolve in superpositions of all allowed possibilities, and measurement defines which branch becomes real for us. A delayed choice simply stretches the gap between action and definition, reminding researchers that quantum descriptions are not sequential narratives but global statements about correlations. What looks like retroactive causation is coherence playing out to its full logical extent. More sophisticated versions use entangled photons to separate the choice from the detection by large distances. One photon's interference pattern disappears or reappears depending on how its distant twin is later measured. No signal travels faster than light, yet the joint data demands a consistent account that includes both events at once. Time ordering becomes a convenience, not an authority. Quantum theory cares about the structure of the experiment as a whole rather than a timeline of individual steps. Such findings have nudged physicists toward deeper questions about the role of information and the flow of time. If the past is defined only when observations complete the circuit, perhaps the universe is less like a chain of dominoes and more like a completed puzzle whose pieces find their places only when all are laid down. Delayed choice tests make that puzzle visible for a moment, showing how fluid the boundary between cause and consequence can be. 13. Quantum teleportation moves states while matter stays put. Teleportation in physics is not the beaming of solid bodies across space, but the faithful transfer of a quantum state from one system to another. The method begins with an entangled pair shared between two sites. The sender performs a joint measurement on the particle to be transmitted, and her half of the pair producing two classical bits of information. When those bits reach the receiver and are applied to his half, the original state reappears exactly, while the sender's copy vanishes in the process. The transfer is perfect and destructive at the same time. This protocol blends three ingredients, entanglement, measurement, and classical communication, into a single elegant recipe. Without the pre-existing entangled link, the data from the measurement would be meaningless. Without the classical message, the receiver would not know which correction to apply. Together they achieve what neither channel could alone. No energy or matter crosses faster than light, yet the identity of the state leaps instantly, rebuilding itself from shared correlations. In laboratories, the procedure has been realized with photons, atoms, ions, and superconducting qubits. Each platform demands exquisite timing and precision, because any lost bit of coherence spoils the reappearance. Achievements include teleporting photons between mountain stations, between satellites and ground receivers, and within quantum chips at nearly perfect fidelity. Each milestone turns a once abstract concept into a working component of the coming quantum network. Conceptually, teleportation rewrites the notion of object permanence. A property of matter can vanish in one spot and surface in another, proving that information rather than substance defines continuity. The process has no science fiction shimmer, yet its calm rigor reveals a deeper magic, the ability to relocate the essence of a quantum entity without moving the body that once carried it. 14. Quantum repeaters stitch a long-distance web of entanglement. Because photons are absorbed or scattered as they travel, direct transmission of entanglement fades exponentially with distance. Classical repeaters simply amplify signals, but amplifying unknown quantum states would destroy them by measurement. The solution is to divide the journey into manageable segments linked by intermediate stations that perform entanglement swapping and purification. Each repeater cleans, verifies, and passes on the coherence, turning fragile local links into robust continental networks. Inside a repeater, stored qubits wait in quantum memory while their partners travel forward. Once a successful connection forms between neighboring nodes, operations merge the segments and extend the reach. Error correction routines remove noise introduced by imperfect detectors and sources, maintaining high-fidelity correlations over thousands of kilometers. Every node acts like a pit stop where the state is refreshed before continuing its non-classical voyage. The engineering challenges remain formidable. Quantum memories must hold states for milliseconds or even seconds without losing phase information, an eternity in atomic time. Entangled photon sources need to operate fast enough that the whole chain can be synchronized despite the random successes and failures of transmission. Progress is steady. Cold atoms, rare earth-doped crystals, and solid-state defects have all served as memory candidates with improving performance. The reward is nothing less than a new layer of infrastructure for secure communication and distributed computing. Once repeaters mature, entanglement could circulate around the planet as freely as radio waves do today, enabling clocks, sensors, and computers to act in concert with quantum accuracy. The web of coherence would become as real as the web of glass fibers beneath our feet. 15. Device-independent cryptography secures keys by pure statistics. Traditional cryptographic schemes assume that hardware behaves as advertised. Quantum device independence removes that trust by using Bell inequality violations as proof of security. If two separated detectors produce correlations strong enough to defy classical explanation, then the key bits derived from their outcomes are guaranteed to be private, no matter how the devices were built or who supplied them. Physics itself becomes the auditor. This principle turns foundational strangeness into practical armor. The very impossibility of local hidden variables ensures that an eavesdropper cannot mimic the pattern without sharing the entanglement. Even a malicious manufacturer who installs hidden channels would fail because the test looks only at statistical outcomes that cannot be faked by classical coordination. Security arises from the structure of the universe rather than the honesty of vendors. Implementations pair entangled photon sources with fast random basis choices and low-latency data links. After many rounds, the parties publicly compare a subset of results to confirm the required violation level, then distill the remainder into a secret key through privacy amplification algorithms. Every parameter, detector efficiency, noise rate, timing window, enters the calculation of how much secrecy can be safely claimed. The process resembles accounting with the laws of physics as the accountant. In a world where information theft grows ever more sophisticated, such guarantees are remarkable. They show that uncertainty, often seen as a weakness, can be engineered into the ultimate defense. Entanglement's refusal to share local copies becomes humanity's strongest lock, protecting data with the same mystery that once puzzled Einstein. 16. Certified quantum randomness turns unpredictability into a resource. Random numbers underlie encryption, simulation, and gambling, yet most classical generators are pseudo-random algorithms that only imitate chance. Quantum processes, by contrast, contain fundamental unpredictability. Still, how can anyone trust that a black box device truly uses quantum effects rather than hidden deterministic circuits? Certification answers this by tying the output to the observed strength of Bell violations. If the statistics break the classical bounds, genuine randomness is mathematically guaranteed. The reasoning is simple but profound. A universe obeying local realism cannot produce certain correlation patterns. Seeing them proves that outcomes are not pre-written. By extracting bits from those outcomes and compressing them through randomness extractors, one obtains sequences that no adversary, not even one entangled with the device, could predict. Randomness becomes measurable, a commodity with provenance. Laboratories now run continuous quantum random number generators based on entangled photons, single photon detection times, and vacuum fluctuations. Certified systems serve banks, research institutes, and online services that need cryptographic strength entropy, rates reach billions of bits per second while maintaining proofs of unpredictability rooted in the foundations of physics. Each bit carries a pedigree signed by non-locality. In effect, quantum randomness factories distill the universe's indeterminacy into usable form. They show that what once seemed a nuisance, the impossibility of predicting every outcome, can be turned into an industry. The noise at the heart of nature becomes a tool for order, ensuring that secrets remain secrets precisely because the cosmos itself refuses full determinism. 17. Quantum Internet prototypes begin to sense a global nervous system. When multiple quantum nodes share entanglement, they can coordinate tasks with efficiency unreachable by classical networks. Early prototypes link laboratories through optical fibers and free space channels, exchanging entangled photons, teleporting states, and synchronizing clocks. The emerging vision resembles a nervous system in which each node both senses and influences the collective state through shared coherence. The Internet gains not only connectivity but awareness of its own correlations. These demonstrations combine diverse technologies: single photon sources, quantum memories, detectors, and routers, each balancing fragility and speed. The key challenge is scalability, extending links without letting decoherence dissolve the network's delicate structure. Hybrid approaches use satellites for long spans and fiber for local distribution, merging methods perfected in communication engineering with insights from quantum optics. Every successful handshake between nodes is a pulse in a growing organism. Applications reach beyond secure messaging. Distributed quantum computing can split algorithms across distant processors. Sensors can compare phases of entangled light to detect tiny environmental changes, and time standards can be synchronized at unprecedented accuracy. Each use case depends on the same underlying principle: that shared entanglement ties remote systems into one logical unit even when miles apart. The first modest webs already hint at what a fully fledged network could feel like. If the 20th century wired the planet with electricity and bits, the 21st may lace it with entanglement. The dream is that distant laboratories, telescopes, and even space missions will operate as coordinated organs of a single quantum infrastructure. The nervous system of the Earth would then extend beyond matter into the realm of correlations themselves. 18. Networked clocks keep time together with entangled precision. Ordinary atomic clocks achieve astonishing accuracy by measuring the frequency of atomic transitions, yet comparing distant clocks requires signals that travel through noisy media. Entangling atoms across locations can synchronize their phases without exchanging conventional pulses. In such networks, a global time reference emerges from the coherence shared among many sites, potentially improving stability by orders of magnitude. Timekeeping becomes a collective quantum act rather than isolated ticking. Experiments with trapped ions and neutral atoms show that entanglement can suppress noise that limits single clock performance. Spin-squeezed ensembles behave as unified oscillators, averaging out individual fluctuations. When connected through entanglement, their readings correlate so strongly that the difference between them reveals variations in gravity or space-time curvature instead of technical error. Precision turns into a map of the planet's subtle rhythms. Building these systems requires careful management of decoherence, since environmental noise quickly washes away the correlations. Optical links must preserve phase information, and feedback algorithms must maintain synchronization in real time. The challenge resembles conducting an orchestra whose instruments are separated by hundreds of kilometers, each playing the same invisible note. Progress suggests that future time networks could redefine the second with unprecedented stability. Beyond metrology, the ability to coordinate clocks this tightly has practical consequences for navigation, geodesy, and fundamental tests of relativity. Entangled time may reveal small drifts in Earth's gravitational field, or even signals from passing gravitational waves. When clocks share a single quantum heartbeat, measuring the universe's tempo becomes a cooperative art. 19. Squeezed light pushes measurements beyond classical limits. Heisenberg's uncertainty principle ties the precision of complementary quantities such as phase and amplitude. Yet it allows trade-offs. Noise can be reduced in one variable at the expense of the other. Light prepared in such an unbalanced state is called squeezed, because the uncertainty ellipse in phase space looks compressed. When this light enters an interferometer, the reduced noise channel aligns with the measured quantity, enabling sensitivities finer than the so-called shot noise limit that governs ordinary beams. Generating squeezed light involves nonlinear optical processes that pump photons into pairs of correlated quanta. The resulting fluctuations cancel in one quadrature and amplify in the orthogonal one. Careful alignment, temperature control, and detection turn the fragile state into a usable probe. The improvement may appear modest in decibels, yet for detectors chasing gravitational waves or testing subtle quantum effects, every fraction counts. Gravitational wave observatories such as LIGO and Virgo already inject squeezed states into their interferometers to sharpen their ears. The approach has extended the observable range of black hole mergers by dozens of percent, a triumph of quantum optics feeding directly into astrophysics. Future instruments plan adaptive squeezing that changes orientation as conditions vary, continually optimizing sensitivity. Quantum light thus extends humanity's reach into the cosmos. The broader lesson is that uncertainty need not be an enemy. By sculpting fluctuations rather than eliminating them, researchers bend quantum noise into a tool. Squeezed states demonstrate that even the limits of measurement are malleable when approached with precision and imagination. 20. Spin-armed squeezing lets atom clouds feel like one superatom. A cloud of atoms can act as a single quantum system when their spins are correlated through interactions or shared light fields. Spin squeezing reduces collective uncertainty in one component of the total angular momentum while increasing it in another, mimicking the principle behind squeezed light. The ensemble then measures magnetic fields or time intervals with accuracy that scales better than the simple square root law of uncorrelated particles. Thousands of atoms become one giant precision instrument. Creating such states involves carefully timed pulses or cavity-mediated interactions that entangle atomic spins without excessive decoherence. Measurement backaction, usually an annoyance, becomes a friend when harnessed to generate the correlations deliberately. Each atom contributes a small piece of information, and the whole cloud amplifies the sensitivity as if every constituent knew how to cooperate. The process turns noise into signal. Spin-squeezed ensembles already enhance atomic clocks, magnetometers, and Hammond interferometers. Experiments demonstrate improvements equivalent to adding many more atoms without physically doing so, a priceless advantage where resources or size are limited. The gain emerges not from brute force, but from shared quantum order. As control improves, these collective states will underpin next-generation sensors capable of detecting faint gravitational or electromagnetic disturbances. The image of a superatom captures more than a metaphor. It hints at how matter can transcend individuality under quantum rules, forming wholes whose behavior cannot be decomposed into parts. Each squeezed ensemble becomes a quiet rehearsal for a universe that itself may operate as a single entangled entity. 21. Noon states promise resolution that defies ordinary optics. Interference patterns set the sharpness limit for many instruments, and classical light divides into photons that behave independently, which caps the achievable resolution. A noon state replaces that independence with a superposition in which all photons take one path or the other in unison, putting n photons in one arm and 0 in the other, and the reverse at the same time. The resulting phase sensitivity scales with the total photon number rather than its square root, a leap that pushes fringes closer together and features into focus that would otherwise blur. The pattern looks like a comb with teeth too fine for everyday beams. The creation of such states is delicate because every lost photon carries away phase information. Nonlinear processes and post-selection can weave the required superposition for small photon numbers, while integrated photonics offers cleaner paths with fewer chances for decoherence to creep in. Detectors must register coincidences with timing that borders on the uncanny, and stability must hold through the entire interferometer. Each improvement raises n by a step, inching the laboratory closer to practical quantum lithography and microscopy. Even when imperfections reduce ideal scaling, partial gains translate into real instruments that read out minute phase shifts. Biological samples and nanostructures that would wilt under bright classical illumination can be probed with fewer quanta yet higher precision, protecting fragile targets while extracting more detail. The same states serve in metrology for measuring tiny motions or fields, turning quantum weirdness into a ruler etched at the scale of waves rather than rods. Sensitivity becomes a design choice rather than a fixed ceiling. The broader message is that structure in light matters as much as intensity. By orchestrating photons into collective modes, One writes instructions into the field about how it should interfere with itself. Noon states illustrate how correlation reshapes what an interferometer can do, trading brute brightness for fragile order. The path forward blends better sources, smarter detection, and clever error mitigation to harvest resolution from coherence. 22. Entanglement entropy measures how much reality is shared. Ordinary entropy counts the number of ways a system can arrange itself while looking the same macroscopically, a measure of ignorance about details. Entanglement entropy takes that logic and applies it to parts of a quantum whole, calculating how much information must be discarded when one ignores a region and focuses on the rest. A value of 0 means perfect separability, while a larger value signals that the parts borrow facts from one another. The number quantifies togetherness with a scale suited to superpositions. Computing this quantity requires tracing out degrees of freedom, a mathematical procedure that removes variables for the discarded region and leaves a mixed description for what remains. The spectrum of that reduced description encodes how strongly the two sides are knotted. In simple chains, the entropy often grows with the size of the boundary rather than the volume, an observation with far-reaching consequences for how information arranges itself in ground states. The boundary becomes a ledger that records shared structure. Experiments probe entanglement entropy indirectly through interference between many copies of the same system, or through randomized measurements that reconstruct moments of the reduced state. Ultra-cold atoms in optical lattices and superconducting circuits have both revealed signatures that match theoretical expectations, including transitions where scaling laws change abruptly. Such measurements turn an abstract quantity into something a camera can see. The numbers map out hidden order that ordinary probes would miss. The concept becomes a bridge between condensed matter and gravity when combined with ideas from holography. In that view, the entropy of a boundary region can be computed by the area of a minimal surface in a higher dimensional geometry, binding information to shape. The formula hints that geometry itself could be bookkeeping for entanglement, with space emerging as a diagram of who shares what with whom. Measurement of a number becomes a glimpse of the architecture of reality. 23. The area law hints that information lives on boundaries. Many gapped quantum systems obey a rule in which the entanglement entropy of a region scales with the size of its boundary rather than its volume. This area law contradicts naive expectations that more bulk should always mean more shared information. The law suggests that correlations organize themselves along surfaces where neighboring degrees of freedom meet. The picture evokes a world where seams matter more than patches. Violations of this law also teach lessons. Critical systems near phase transitions and highly excited states can show entropy that grows beyond the boundary, signaling long-range entanglement that floods the interior. Such exceptions do not break the concept but illuminate the mechanisms that enforce it in calmer phases. The contrast between obedient ground states and rebellious critical points becomes a diagnostic tool. Scaling turns into a fingerprint for quantum order. The area trend resonates with gravitational physics, where black hole entropy scales with horizon area rather than volume. This parallel inspired the holographic principle, which proposes that the description of a region can be stored on a lower dimensional surface with no loss of information. Entanglement thus links the behavior of cold materials to the thermodynamics of space-time, a surprising handshake between laboratory and cosmos. Boundaries become carriers of both heat and a meaning. Practical implications follow. Tensor network methods such as matrix product states exploit the area law to compress many body wave functions efficiently, enabling simulations that would otherwise be impossible. The computational success confirms that typical low-energy states do not spray entanglement indiscriminately across the bulk. The economy of boundaries becomes a resource for both theory and engineering. 24. Holographic arguments link geometry with entanglement. In holographic duality, a quantum field theory without gravity living on a boundary corresponds to a gravitational theory in a higher dimensional bulk. The dictionary between the two pictures equates entanglement entropy in the boundary with areas of extremal surfaces in the bulk, giving a geometric recipe for a quantum information quantity. Curves and surfaces encode who is entangled with whom, turning shape into a ledger of correlation. Space is no longer a stage but an account book. When the boundary state changes, the corresponding bulk geometry adjusts as if pulled by invisible strings tied to entanglement patterns. Adding or removing correlations can expand or pinch regions of space, while quantum error correction language explains how bulk information hides redundantly in boundary degrees of freedom. The code protects against local erasures, and mirrors the stability of space-time against small disturbances, geometry becomes a robust message written across many carriers. This framework reframes puzzles about black holes and information loss. Radiation entangled with the interior can be modelled through boundary correlations, and the recovery of information appears as a decoding problem rather than a violation of thermodynamic sense. The Page curve that tracks entropy over time arises naturally when quantum extremal surfaces are allowed to compete, suggesting a graceful return of lost data. Entanglement is the thread that sews disappearance back into memory. Although the duality is best understood in specialized settings, its influence reaches widely. It guides intuition about how complex quantum systems organize themselves and inspires algorithms for simulating them. The idea that distance might measure similarity of quantum states rather than separations of points invites a fresh reading of locality. Geometry and information stop being rivals and become two dialects of the same language. 25 ER equals EPR proposes wormholes as entangled bridges. A bold conjecture links two famous ideas, Einstein-Rosen bridges and Einstein-Podolsky-Rosen pairs, asserting that every entangled pair corresponds to a tiny non-traversable wormhole. The statement does not claim that signals cross faster than light, but that the mathematical structures share a common ancestry. Entanglement would then be the fabric that sews distant regions together, while wormholes would be the geometric shadow of that sewing. The map trades threads for tunnels. Models in holographic settings provide playgrounds where such correspondences can be tested. Coupling two identical systems in special ways creates bulk geometries that look like two mouths joined by a throat, and operations that change entanglement translate into deformations of that throat. In controlled protocols, adding appropriate interactions can even produce traversable wormhole analogues, where information effectively teleports from one side to the other. The passage respects causality because the ingredients arrange a route consistent with known limits. The picture softens conceptual tensions between non-local correlations and space-time respect for light speed. If the link between entangled partners is geometric rather than a messenger, there is no need for superluminal travel to explain instant coordination. The non-traversability of generic wormholes guards communication limits, while still accounting for connectedness. The bridge is there, yet not a highway. While evidence remains circumstantial outside specialized theories, the intuition has shaped how researchers think about both quantum gravity and quantum information. It suggests that solving problems on one side translates immediately into progress on the other. Each new protocol that moves quantum states without moving matter looks like a small echo of a tunnel beneath space. 26. Traversable wormhole analogues appear as controlled teleportation. In certain engineered systems, carefully chosen interactions can mimic the effect of sending a signal through a wormhole. Two entangled systems are prepared in a state similar to a thermofield double, and a brief coupling introduces a negative energy shock that opens the throat for a moment. A qubit inserted on one side then emerges on the other after a delay that matches the travel time predicted by the effective geometry. No laws are broken because the construction is equivalent to a teleportation circuit executed with a particular twist. Experiments with quantum processors have implemented small-scale versions of this idea. Correlations grow under scramblings that spread information through each system, and the special interaction stitches the halves so that a message survives the chaos and reassembles on the far side. Observables trace the path as if a particle had crossed a tunnel, though what truly moves is a pattern of correlations. The emergence resembles watching a story told in two languages at once. The point is not that a door through space has been found, but that geometry and computation can be two faces of the same process. Designing the couplings teaches how to route quantum information through noise, while the geometric metaphor clarifies why only certain patterns succeed. This synergy enriches both fields, giving gravity pictures to lab protocols and giving hardware developers a visual intuition for abstract algorithms. The wormhole becomes a blueprint for resilience. As systems grow in size and coherence, these demonstrations will test deeper aspects of scrambling, chaos, and error correction. The hope is to paint a continuous path from tabletop chips to principles that govern black holes. Each working circuit that looks like a tunnel offers confidence that the dictionary between geometry and entanglement spells real sentences. 27. The Page curve tells how black holes give information back. When a black hole radiates, naive calculations predict that its radiation remains featureless until the end, leading to information loss and a conflict with quantum mechanics. The page curve corrects this picture by showing that the entropy of the radiation rises at first and then falls as correlations with the fainter hole allow information to leak out. The turning point marks when the outside holds more of the secret than the inside. The curve bends toward restoration rather than oblivion. Recent progress derives this behavior using tools from quantum extremal surfaces and replica tricks. By allowing additional saddles in the gravitational path integral, the calculations reveal islands that count as part of the radiation's entanglement partner, effectively relocating pieces of the interior to the outside description. The resulting entropy matches the expected page curve without violating known principles. Information never truly disappears, it only hides in a way that the revised accounting can see. This development reframes the long debate about paradoxes at horizons. Rather than invoking dramatic failures of smooth geometry, the resolution relies on subtle rearrangements of what counts as where in the bookkeeping of entanglement. The mathematics does the heavy lifting while physical intuition follows afterward. The black hole becomes less a furnace that burns data and more a vault that slowly releases it through structured correlations. While a full microscopic model for every case remains a goal, the shift from despair to constructive calculation has energized the field. The curve is now something to derive and measure in analog systems rather than a cartoon of contradiction. Each successful derivation strengthens the suspicion that quantum gravity respects unitarity in ways that classical pictures only partly capture. The story curves toward coherence. 28. Hawking radiation looks like a book torn into entangled halves. Pairs of quanta form near the horizon through fluctuations, with one escaping to infinity while the other falls inward. The escaping partner carries heat that reveals the black hole's temperature, while the infalling partner remains trapped behind the horizon. The two are entangled, which means the outside radiation alone appears thermally mixed even though the total state is pure. The pages of the story are split between two libraries. As more radiation escapes, the outside pile grows, and correlations build among the emitted quanta themselves and between them and the interior. Early on, the radiation looks almost featureless because most correlations remain hidden within the whole. Later, as the page time passes, the outside collection begins to carry enough structure that careful observers could, in principle, reconstruct the message. The book starts to come back together without breaking any rules. Toy models show how this process could work in systems that mimic horizons or in solvable gravitational theories. Quantum information tools such as error correction and entanglement wedges explain how data stored behind a boundary can be reconstructed from a sufficiently large share of exterior degrees of freedom. The analogy aligns with what teleportation circuits teach in the laboratory. The halves may be separated by geometry, yet algebra keeps them married. The picture undermines the idea that horizons must either burn or forget. Instead, the horizon becomes a dynamic interface that trades correlations with its environment according to strict rules. Radiation gains structure the way steam from a kettle might, not through magical patterns imprinted on each molecule, but through global constraints on the whole cloud. The warmth carries memory in disguise. 29. Entanglement wedges promise that lost data can be rebuilt. In holographic settings, a boundary region can reconstruct information about a specific bulk region known as its entanglement wedge. The wedge is defined by extremal surfaces that bound where reconstruction is possible, giving a concrete map from accessible data to hidden structure. Grow the boundary region and the wedge reaches deeper, eventually engulfing features that once lay beyond reach. Recovery becomes a geometric right rather than a miracle. The mathematics parallels quantum error correction. Bulk operators act like logical qubits encoded across many boundary degrees of freedom, so that losing a portion of the boundary still leaves the message intact. Different boundary regions can sometimes reconstruct the same bulk operator, illustrating redundancy that protects against erasures. The wedge therefore describes which sets of observers can do which reconstructions. Access turns into shape. This framework clarifies puzzles about how information emerges from behind horizons. If the entanglement wedge of the radiation includes parts of the interior after the page time, then observers with enough of the outside can decode what fell in. The conclusion does not grant superpowers, but follows from the code structure woven through the boundary theory. Learning where wedges lie becomes a way to chart who can know what. The idea also encourages new protocols for experiments on quantum processors. Circuits that mimic encoding and reconstruction demonstrate wedge-like behavior at small scales, turning geometry into a testable property of entanglement patterns. Each success lends weight to the belief that space-time itself operates as a code. What looks like emptiness could be densely written with parity checks. 30. The firewall puzzle challenges the smoothness of horizons. An argument once claimed that unitarity, locality, and the equivalence principle cannot all hold at black hole horizons. If late radiation must be entangled with early radiation to preserve information, and field theory near the horizon also demands entanglement across the horizon for smoothness, then monogamy of entanglement seems violated. The proposed fix placed a searing wall of high-energy quanta at the horizon, breaking smooth passage for infalling observers. The tranquil event horizon became a furnace. Subsequent work softened this dire picture by refining what counts as where in the bookkeeping of entanglement. Entanglement wedges and state-dependent reconstructions allow the same degrees of freedom to play different roles for different observers without double counting. The interior can be encoded in the exterior in a way that preserves monogamy once the code structure is honoured. The fire recedes when the accounting is done with care. The debate remains a healthy engine for new ideas. It forced clarity about assumptions often taken for granted, such as how measurements by different observers should be combined and which operators belong to which algebras. It also spurred searches for experiments that, while not probing astrophysical horizons directly, could simulate the logic in laboratory systems. Conceptual friction turned into technical progress. Whether any remnant of the firewall survives in exotic scenarios is an open question worth exploring. What has changed is the mood, from an apparent contradiction to a toolkit for threading the needle among cherished principles. Horizons may still hold surprises, yet they need not be walls of flame. They can be subtle gates whose secrets are written in entanglement. 31. Gravitationally induced entanglement could reveal quantum gravity. If two tiny masses become entangled solely because they feel each other's gravitational pull, that would prove gravity itself must be quantum. Classical gravity would only correlate them without creating true quantum superpositions. The proposed tests suspend micrometer-scale objects in isolation, place them into spatial superpositions, and let gravity alone act between them. If their spins later show non-classical correlations, the result would be a whisper from quantum gravity in a tabletop setting. The technical demands are extreme. Isolation from vibrations, magnetic noise, and stray photons must reach levels once thought absurd. Yet rapid advances in levitated optomechanics and matter wave interferometry are bringing the idea within reach. Each improvement in coherence time or cooling brings the masses closer to the regime where gravitational interaction competes with decoherence. The experiment would not need Planck scale energies, only exquisite setuts. The logic rests on entanglement as a witness. If gravity transmits no quantum information, it cannot produce an entangled state between two systems. Observing entanglement would therefore exclude purely classical mediators and imply a quantum field underlying space itself. The test would transform metaphysical arguments into measurable data. Such an achievement would mark the first tangible handshake between quantum mechanics and general relativity. Instead of building colliders the size of planets, humanity could glimpse quantum gravity through fragile dust motes balanced on light. The discovery would show that even the soft pull of weight obeys the same probabilistic rhythm that governs atoms, uniting the small and the vast in one experiment. 32. Massive objects might entangle through gravity alone. Experiments have already entangled photons, electrons, and atoms. Now researchers aim at heavier systems approaching 1 trillion atomic mass units. The heavier the objects, the more strongly they couple through gravity, but also the harder it becomes to shield them from noise. Proposals use tiny spheres or membranes suspended by lasers, cooled to near absolute zero, and separated by micrometers. If their motions correlate beyond classical prediction, the source could be gravity itself, acting as a quantum link. Each test pushes the definition of massive downward toward the smallest weight that still bends space-time detectably. Observing quantum correlations in such objects would extend the known territory of superposition far beyond molecules and into the mesoscopic world. It would also close the gap between quantum optics and precision measurement, turning gravitational interaction into another tool for quantum control. The challenge resembles juggling planets made of smoke, mechanical stability, decoherence from residual gas, and readout sensitivity must all align at once. Researchers exploit optical cavities and superconducting circuits to amplify tiny displacements until they register as measurable phase shifts. The slightest thermal fluctuation could ruin hours of preparation, making each successful run a small miracle of engineering. If confirmed, gravitational entanglement among massive bodies would dissolve the border between mechanics and field theory. Space-time curvature would join the family of quantum resources alongside light and spin. Such an outcome would not only reveal quantum gravity indirectly, but also expand the palette for future quantum technologies that use mass and motion as carriers of information. 33. Optomechanical mirrors show quantum behavior in heavy systems. A mirror only a few microns wide can act like both a mechanical oscillator and a participant in quantum experiments. When light bounces off it inside an optical cavity, each photon imparts a tiny push. Collectively, these pushes create a measurable vibration. Cooling the mirror's motion close to its quantum ground state allows researchers to see phenomena once reserved for atoms, superposition, squeezing and entanglement, now enacted by billions of atoms moving as one. The field of optomechanics builds on this principle to study the boundary between the quantum and the classical. Laser cooling removes thermal motion until the mirror's displacement fluctuates purely because of zero-point energy. Quantum back-action, in which measuring the position disturbs the momentum, becomes the dominant noise source. Balancing measurement and disturbance yields sensitivities that reach the standard quantum limit and sometimes surpass it with clever feedback. Optomechanical systems serve as testbeds for fundamental physics and as components for quantum technologies. They can link microwave and optical photons, acting as translators between quantum computers that operate at different frequencies. They also enable precision sensors capable of detecting weak forces and accelerations far below traditional limits. Each device embodies the meeting of photons and phonons, light and mechanical sound, within one coherent story. At a philosophical level, the moving mirror reminds observers that mass does not guarantee classicality. A system containing trillions of particles can still obey a single wave equation if noise is tamed. What matters is isolation and coherence, not size. The mirror becomes a quiet proof that macroscopic is a human word, not a physical boundary. By the way, if you like and subscribe to my video, this is the most effective way to support me. 34. Macroscopic superposition test where quantum ends. Schrödinger's cat was a thought experiment. Today, scientists build its analogues with molecules, mechanical resonators, and superconducting circuits, creating a state where a visible object exists in two places or motions at once, forces quantum theory into the realm of human senses. If such superpositions persist without collapse, quantum rules have no natural cutoff. If they decay faster than expected, the data may reveal hidden mechanisms that restore classical order. Experiments grow ever bolder. Interference of molecules with thousands of atoms, vibrating cantilevers holding superposed mechanical energy, and superconducting loops carrying currents in opposite directions simultaneously. Each setup measures visibility of interference fringes, while fighting decoherence from heat, air, and stray fields. Success pushes the boundary of quantum upward in scale, showing that size alone does not end the dance. Alternative models predict spontaneous collapses proportional to mass or complexity. Observing or refuting such deviations would test whether quantum mechanics is exact or emergent. Precision control over isolation times allows bounds to tighten steadily. Even null results teach by confirming that reality remains probabilistic no matter how large the experiment becomes. The quest is poetic as well as technical. Watching a dust grain interfere with itself or a mirror vibrate in contradictory directions recalls the original astonishment of the double slit. Each gram of matter brought under quantum control stretches the imagination and whispers that certainty was never built into the laws of nature, only into habits of thought. 35. Decoherence turns vibrant quantum music into classical noise. A quantum system in superposition behaves like a chord with many notes playing at once. When it interacts with the environment, stray degrees of freedom pick up information about which note is which, and the harmony fades into a single tone. This process, decoherence, explains why macroscopic objects rarely display interference. It converts possibilities into probabilities without invoking conscious observation, grounding the transition from quantum to classical in physical interactions. Mathematically, decoherence spreads phase information into the environment, making it effectively inaccessible to local measurements. The system's density matrix loses its off-diagonal elements, erasing interference patterns, even though the full state of system plus environment remains pure. In practice, the environment becomes a vast measurement apparatus whose records cannot be erased. The result feels like collapse, though it arises from ordinary dynamics. Controlling decoherence is the main obstacle to building quantum technologies. Cooling, shielding, and error correction all aim to slow the rate at which information leaks away. Different platforms, ions, superconducting circuits, photons, suffer from distinct sources of noise, from magnetic fluctuations to photon loss. Every qubit is a small sanctuary that must be kept intact against a storm of entangling influences. Philosophically, decoherence rescues realism without mysticism. It shows that classical behavior emerges not from ignorance, but from the environment's overwhelming capacity to monitor systems. The loss of phase coherence is not a flaw in quantum law, but its natural consequence when too many eyes watch at once. 36. Quantum error correction protects fragile superpositions. Because decoherence is inevitable, the survival of quantum information depends on encoding it redundantly across many physical systems. Quantum error correction does this without violating the no-cloning theorem by storing logical qubits in entangled states of many physical qubits. Errors on individual components can be detected and reversed by syndrome measurements that extract only the error pattern, not the encoded information itself. The concept turns fragility into manageable bookkeeping. Codes such as the surface code, color code, and concatenated code define networks of qubits connected by stabilizer checks. Periodic measurements of these checks reveal where noise has struck, allowing real-time correction. The mathematics resembles that of classical error correction, but expanded into the complex domain, with extra care for the phase relationships that define quantum states. Successful decoding restores coherence as if the disturbance had never happened. Implementations already stabilize small logical qubits for seconds, a lifetime compared to unprotected coherence times. Superconducting processors, trapped ions, and neutral atoms all run early versions, demonstrating exponential suppression of errors as code distance increases. Each additional layer of protection moves computation from the laboratory toward reliability required for practical use. Quantum memory ceases to be an oxymoron. Beyond technology, error correction feeds back into theoretical physics. Holographic duality interprets spacetime itself as an error-correcting code, where bulk information is protected by redundant encoding on the boundary. The same mathematics that keeps qubits alive might also keep the universe consistent. In that sense, every stable computation rehearses the logic of cosmic stability. 37. Surface codes store quantum information in global patterns. Among the many error correction schemes, surface codes dominate current research because they use only local interactions laid out on a two-dimensional grid, ideal for hardware fabrication. Logical qubits are defined not by single elements, but by loops of correlations that wrapped around the lattice. As long as errors remain confined and do not form a continuous path across the surface, the encoded information survives intact. The resilience arises from topology rather than brute force. Each physical qubit interacts only with its neighbors to measure parity checks that detect bit and phase flips. The outcomes of these stabilizers form patterns resembling frost crystals, and decoding algorithms interpret them to infer the most likely error configuration. Because correction relies on local data, the system scales well with size. Larger surfaces mean longer logical lifetimes. Experiments have already demonstrated logical operations and repetitive cycles of detection and correction on small lattices. The goal is to reach error thresholds below 1%, where the code becomes self-sustaining under continuous operation. Once that point is crossed, logical qubits can live arbitrarily long by adding more physical qubits. Reliability stops being a dream and becomes a function of scale. The beauty of surface codes lies in their geometric intuition. Information hides in patterns that cannot be erased by local tinkering, echoing the way a donut's hole survives among small deformations. Computation turns into topology, and resilience becomes geometry made digital. 38. Entanglement monogamy limits who can share the deepest bonds. In quantum mechanics, strong entanglement between two parties forbids equally strong entanglement with a third. This property, called monogamy, sets boundaries on how correlations distribute across many body systems. It prevents the kind of collective coordination that classical systems can easily share. forcing quantum relationships to organize into networks with specific hierarchies. The rule keeps quantum information faithful to its partners. Mathematically, measures like concurrence or entanglement of formation obey inequalities that encode this exclusivity. If one pair saturates the bound, all others must weaken. The effect shapes how quantum communication protocols divide resources and how security arises in key distribution. Eavesdroppers cannot entangle themselves strongly with both legitimate users at once. Monogamy becomes a guardian of privacy written into the fabric of correlation. In multiparticle physics, the same constraint influences the structure of states such as Greenberger, Horner-Zeilinger, and W states, determining how robustness and fragility trade off. Engineers designing quantum networks must navigate these limits when distributing entanglement across nodes. Too much intimacy between two parties leaves less for others, making resource allocation an exercise in relational geometry. The idea extends beyond metaphor. Monogamy ensures that quantum entanglement cannot be copied or spread arbitrarily, a fact underlying the no-cloning theorem and the security of quantum cryptography. The universe enforces loyalty among its correlations. Once two systems commit to each other fully, outsiders are forever excluded from their perfect trust. 39. The quantum Zeno effect freezes motion by constant watching. Repeated observation can halt evolution, a paradoxical consequence of measurement disturbing state changes. If a system is checked often enough to see whether it has decayed or transformed, each projection resets its wave function, and the probability of change shrinks. In the limit of continuous measurement, the system can remain locked in its initial state, as if time itself hesitated under scrutiny. The effect draws its name from the philosopher who argued that an arrow in flight is motionless at every instant. Experiments with trapped ions and cold atoms confirm this behavior. Rapid sequences of gentle measurements prevent transitions that would otherwise occur spontaneously. The more frequently the system is interrogated, the slower its evolution becomes, matching theoretical predictions with high precision. Measurement acts not only as discovery but as control. This phenomenon has practical applications in quantum control and computation. Carefully timed observations or coupling to ancilla systems can stabilize desired states against unwanted dynamics. The same logic underlies dynamical decoupling, where periodic pulses refocus coherence by slicing time into protective intervals. Watching becomes a way to guide. The quantum Zeno effect reframes the act of measurement from passive to participatory. The universe responds to curiosity, not with revelation alone, but with modification. The arrow may still fly, but only when observation loosens its grip. 40. Indefinite causal order twists before and after into one. Ordinary events follow a strict sequence. Cause precedes effect. Quantum mechanics, when applied to processes themselves, allows superpositions where the order of operations is not fixed. Two actions, A and B, can occur in a state that is simultaneously A before B and B before A. Experiments using photons routed through interferometers with switchable paths have realized such indefinite causal orders, showing computational and communication advantages. The notion of which happened first loses absolute meaning. In these setups, the control of the path acts as a quantum switch, placing circuits into superpositions of different time orders. Tasks that require communication in both directions classically can sometimes be completed in one round, thanks to the overlap of orders. The gain is modest numerically, but profound conceptually. Causality itself becomes a quantum variable. Mathematically, process matrices replace fixed channels describing probabilities for outcomes without presupposing temporal hierarchy. The framework remains consistent and free of paradox, showing that indefinite order does not entail contradictions or retrocausality. It merely broadens what is meant by correlation. Logic bends but does not break. Such experiments touch the edge of future physics, where quantum gravity might blur time and space beyond recognition. If order can exist in superposition, then space-time itself might be a derived notion rather than a stage. The quantum switch becomes a rehearsal for a universe where sequence is secondary to structure. 41. Process matrices describe events with no fixed timeline. The mathematical language that accommodates indefinite causal order replaces time-ordered chains with process matrices, objects that capture correlations among operations without presuming which one comes first. Each participant inserts a local quantum operation, and the process matrix assigns probabilities to joint outcomes, while staying consistent with basic constraints like no superluminal signaling. The framework generalizes both quantum channels and quantum states, offering a unified stage where order itself becomes a variable. What distinguishes a process matrix from an ordinary circuit is its neutrality regarding direction. Classical reasoning demands arrows pointing forward, yet the process formalism deals only with conditions that must hold globally. If one operation depends on another in some fraction of the experimental runs, that dependency appears statistically, not as a hardwired chronology. The result is a theory capable of describing scenarios where time behaves like an entangled resource rather than a parameter. Experiments using photonic interferometers and polarization controls have implemented examples known as the quantum switch, where two gates act in superposition of sequences. Measurements of interference patterns verify predictions that cannot be explained by any definite order of operations. The data agree precisely with the process matrix description, showing that quantum mechanics itself does not insist on a universal clock. Beyond conceptual intrigue, this approach hints at new computation strategies. Algorithms exploiting indefinite order can outperform those limited by strict sequence, reducing the number of communication rounds required between nodes. In the broader sense, process matrices expose how the flow of information may be deeper than the flow of time, a notion likely to matter once gravity and quantum theory meet on equal footing. 42. Retrocausal models let future choices echo into the past. A minority of physicists explore whether quantum correlations could be explained by influences that travel backward in time. In retrocausal interpretations, a measurement setting might help determine the state of the particle before the measurement occurred. This inversion removes the need for instantaneous effects across distance while preserving local dynamics at the cost of giving up a one-way arrow of cause. The universe would then resemble a tapestry woven from both ends simultaneously. Mathematically, such models use boundary conditions set in both the past and the future, allowing events to be determined by constraints spanning the whole experiment. The particle's properties at emission would depend on what measurement it will face later, and this dependence could reproduce quantum statistics without non-local signaling. The story sounds paradoxical only because human perception insists that influence must flow forward. Testing retrocausality is subtle. Experiments that close loopholes or randomize choices faster than light could communicate have already made standard local realism untenable, but retrocausal accounts survive by construction. The challenge lies in finding distinct quantitative predictions, such as minute asymmetries or correlations with delayed settings, that ordinary quantum mechanics forbids. If found, they would revolutionize our understanding of time's directionality. Even without decisive evidence, retrocausal ideas serve as intellectual probes. They remind researchers that causation is not a primitive ingredient of quantum theory, but an emergent pattern observed at macroscopic scales. Whether the future truly whispers to the past or merely appears to when viewed through entanglement, the thought expands the boundary of what explanation could mean. 43. Bohmian waves steer particles with a non-local pilot. David Bohm's interpretation restores determinism by proposing that particles have precise positions guided by a quantum potential derived from the wave function. The wave acts as a pilot field that spreads instantly through space, steering each particle along a trajectory consistent with observed probabilities. This non-local pilot wave picture reproduces all measurable predictions of standard quantum mechanics, while offering a clear ontology. Particles move, waves guide. The guidance equation couples every particle to the full configuration of the system, meaning that a change in one place can alter the pilot field everywhere. Non-locality remains, but hidden under a deterministic surface rather than probabilistic collapse. In two-slit experiments, particles pass through one slit while the pilot wave traverses both, producing the familiar interference pattern through the wave's influence on trajectories. Each detection spot has a definite cause, even if the pattern as a whole remains statistical. Critics point out that the theory introduces a preferred reference frame for the instantaneous guidance, seemingly at odds with relativity. Extensions attempt to reconcile the two by embedding the pilot field in relativistic or field-theoretic structures. Supporters argue that the clarity about what exists outweighs the discomfort of non-local communication, since non-locality is present in standard quantum theory anyway. Bohmian mechanics thus trades mystery of measurement for mystery of motion. Beyond philosophy, pilot wave ideas inspire computational tools and analog experiments. Hydrodynamic systems where droplets bounce on vibrating fluids show similar guided trajectories, providing intuition for wave-particle duality. Whether or not Bohm's model simply describes reality, it continues to offer a concrete visualization of quantum processes, paths traced through a sea of probability. 44. Mobius. Many worlds spreads outcomes into parallel branches. Hugh Everett's interpretation removes collapse entirely, asserting that all possible outcomes of a quantum event occur in parallel, each in its own branch of the universal wave function. When a measurement happens, the observer becomes entangled with the system, splitting into versions that record different results. Nothing truly random happens. Instead, reality continuously subdivides into non-interacting copies. Probability becomes a measure of branch weight, not of ignorance. This picture eliminates non-local communication, because every correlation is encoded globally in the universal state. Entanglement no longer transmits information instantaneously, it merely correlates histories that diverge from a common past. Each observer experiences a definite outcome while unaware of counterparts in other branches. Decoherence ensures that interference between large branches vanishes, giving the appearance of a single classical world. Critics object that the interpretation multiplies entities beyond necessity, and offers no mechanism for why some branches feel real while others do not. Defenders reply that simplicity lies in the equations, not in human taste. The Schrödinger equation never required pruning, so none is applied. Probability can be recovered from decision theory or symmetry arguments, turning the wave function into a universal law of structure rather than chance. Whatever one's stance, the many worlds view reshapes imagination. It transforms quantum events from dice rolls into bifurcations of reality, suggesting that the universe continually explores every allowed path. Entanglement becomes the record of shared ancestry among worlds, a silent genealogy branching through Hilbert space. 45. Objective collapse ideas add real flashes to end superpositions. Objective collapse theories modify the Schrödinger equation so that superpositions spontaneously localize after a random time, with rates that increase with system size. The Ghirardi-Rimini-Weber and continuous spontaneous localization models introduce noise fields that cause wave functions to collapse without observers. Microscopic particles remain unaffected for ages, while macroscopic bodies collapse almost instantly, producing the appearance of classical reality. The world gains definite outcomes through intrinsic instability rather than measurement. These theories make predictions that diverge slightly from standard quantum mechanics. The additional noise leads to tiny heating effects, spontaneous radiation, or blurring in interferometers at specific scales. Experiments with ultra-cold cantilevers, trapped nanoparticles, and precision spectroscopy continue to narrow the allowed parameter space. Each null result tightens the leash on collapse rates, yet the possibility remains open within certain bounds. The motivation behind such models is both philosophical and empirical. They offer a concrete resolution of the measurement problem by introducing physical events instead of observer-dependent collapse. The cost is a small violation of energy conservation and a new constant of nature governing collapse frequency. Whether that price is worth paying depends on future data. If evidence for objective collapse were ever found, it would signal a new layer of physics bridging quantum and classical domains. Reality would then flicker with spontaneous decisions, tiny sparks of definiteness that ripple through the continuum of possibilities. The dream of deterministic wave evolution would yield to a universe that occasionally chooses. 46. Contextuality shows that properties depend on the whole setup. Cauchy and Specker proved that in quantum mechanics it is impossible to assign predetermined values to all observables in a way that stays consistent across different measurement contexts. The outcome of an observable depends on which other compatible quantities are measured alongside it. Contextuality thus undercuts the notion that systems carry independent attributes waiting to be revealed. Instead, measurement arrangements co-create the results. The experiment and the object form one indivisible whole. Recent tests with photons, neutrons, and trapped ions have confirmed contextual correlations predicted by theory. Violations of non-contextual inequalities mirror the violations of Bell inequalities but without spatial separation, emphasizing that quantum weirdness is not about distance but about dependence. Even single particles exhibit the trait when probed through cleverly designed sequences of operations. The behavior cannot be mimicked by hidden variables that respect classical logic. Contextuality has become a recognized resource in quantum computation. Certain algorithms and state preparations gain their power precisely from configurations that would be impossible in a non-contextual world. Measuring contextuality provides a quantitative handle on the magic that fuels quantum speedup. What once seemed an embarrassment of theory now measures computational potential. Philosophically, contextuality tells us that properties are relational rather than intrinsic. An electron's spin direction is not written on its surface, but it emerges from interaction with the chosen frame of reference. Reality, viewed through this lens, is participatory at its core, shaped by the questions it allows to be asked together. 47. Quantum steering lets one lab shape another lab's state. Steering refers to the ability of one party, by choosing different measurements on their half of an entangled pair, to prepare different ensembles of states for the distant partner. Einstein and Schrödinger debated this idea in the 1930s, wondering whether one system could remotely steer the other's reality. Modern experiments confirm that steering is real but bounded. It cannot transmit information faster than light, yet it provides stronger correlations than any classical mixture could achieve. The phenomenon bridges entanglement and Bell non-locality. It requires trust in one party's measurements but not the others, making it valuable for asymmetric quantum communication where only one device is certified. Demonstrations use polarization-entangled photons, squeezed light, and atomic ensembles to verify steering inequalities. Violations of these inequalities guarantee the presence of genuine entanglement, even when one detector's behavior is unknown. Practically, steering enhances quantum key distribution and network verification. If Alice can steer Bob's state in a way no classical strategy can imitate, then Bob knows they share entanglement without trusting Alice's apparatus. The concept thus blends fundamental curiosity with operational security, turning paradox into protocol. In deeper terms, steering reminds researchers that influence and information need not coincide. One system's choices can mold the statistics seen by another without carrying a message. The result is control without communication, a quiet exhibition of how flexible quantum connectedness can be. 48. Wigner's friend raises questions about what counts as a fact. Eugene Wigner imagined a friend performing a quantum measurement inside a sealed lab while he observed from outside. For the friend, the outcome is definite. For Wigner, the combined lab and system remain in superposition. Which description is correct? The paradox exposes a tension between subjective experience and objective wave functions. If quantum theory applies universally, both viewpoints must coexist without contradiction, yet reconciling them strains common logic. Recent thought experiments and even small quantum tests have pushed the idea further. Multiple observers can become entangled with different outcomes, leading to situations where they would assign conflicting realities to the same event. The Frauchiger-Renner argument formalizes this, showing that assuming universal validity of quantum mechanics, single outcomes, and logical consistency cannot all hold simultaneously, something must give. These scenarios do not yield practical contradictions, but highlight the limits of classical reasoning about observation. Some interpretations resolve the puzzle by assigning each observer their own branch or context, others by restricting where the wave function applies. The discussion refines the meaning of measurement and fact rather than discarding the theory. In a broader sense, Wigner's friend demonstrates that reality's definiteness may be perspectival. Facts solidify relative to observers who share a communication channel but may differ elsewhere. The universe could host overlapping yet internally consistent accounts, each true within its domain, an unsettling but increasingly plausible view of coexistence. 49 of Frauchiger and Renner argue that universal facts may fail. Building on Wigner's friend, Daniela Frauchiger and Renato Renner proposed a self-consistent thought experiment showing that if quantum mechanics applies to both observers and observed, then assuming a single objective reality leads to contradiction. In their scenario, multiple agents reason about each other's measurements using quantum rules and reaching compatible conclusions about the same event. The inference chain collapses under its own logic. The result does not mean quantum theory is wrong, it means that certain classical assumptions about truth cannot survive in its domain. Either measurements do not have single outcomes for all observers, or quantum theory ceases to hold universally, or reasoning across perspectives must follow new rules. Each choice demands a revision of the foundations. Experimental analogues have simulated simplified versions of the paradox with photons and qubits, confirming that the statistical structure required for the contradiction can indeed be realized. The physical system behaves as predicted by standard quantum mechanics, which means the tension arises not from experiment but from interpretation. The laboratory enacts logical paradox rather than physical impossibility. This conclusion pushes philosophy of science toward relational and perspectival frameworks. Knowledge may depend not only on information possessed, but on who possesses it and how they interact. Universal facts give way to networks of consistent partial truths stitched together where communication allows. Quantum mechanics thus becomes not merely a theory of matter, but a mirror for the limits of objectivity itself. 50. Entanglement appears in superconducting circuits on tiny chips. Superconducting qubits made from Josephson junctions trap and control currents that flow without resistance, forming artificial atoms large enough to see under a microscope yet delicate enough to exhibit quantum behavior. Coupling these circuits through microwave resonators creates controllable entanglement with gate fidelities exceeding 99%. What once required atomic physics setups now fits on a silicon chip cooled to a fraction of a degree above absolute zero. The principle rests on the nonlinearity of the Josephson junction, which provides discrete energy levels and tunable coupling. Microwave pulses manipulate these levels to perform logic operations and entangle multiple qubits. Fast electronics handle timing with nanosecond precision, while cryogenic shielding protects against stray radiation. The hardware turns supercurrents into qubit carriers, merging quantum coherence with integrated circuit engineering. Arrays of such qubits already run short quantum algorithms, simulate molecules, and test error correction codes. Scaling remains difficult because coherence times shorten with complexity, but progress is steady. Each new generation increases the number of coupled qubits and the quality of gates, approaching the threshold for fault-tolerant operation. Entanglement becomes an industrial product measured in percentages and yields. The success of superconducting platforms demonstrates that quantum phenomena need not hide in esoteric corners of physics. They can live on manufactured chips, engineered and optimized like transistors once were. The boundary between laboratory curiosity and technology blurs. Entanglement becomes a component, not a mystery. 51. Trapped ions hold near-perfect quantum memories. Ions confined in electromagnetic traps float in near-perfect vacuum, isolated from everything but the electric fields that suspend them. Their internal energy levels provide exceptionally stable qubits, and their motion in the trap allows controlled interactions through shared vibrational modes. Laser pulses tuned with astonishing precision perform gate operations, entangle ions, and read out results without destroying coherence. The trapped ion platform is often considered the gold standard for quantum fidelity. Decades of development have refined each element of the technique. Cooling lasers damp motion to the ground state, radio frequency fields shape potential wells, and ultra-stable oscillators synchronize pulses at sub-nanosecond timing. Errors per gate have dropped below 1 in 10,000, performance unmatched by most solid-state systems. Strings of ions can act as small quantum registers, with logic operations mediated by collective phonon modes that play the role of a shared bus. Scalability remains the challenge. As the number of ions grows, controlling crosstalk and maintaining uniform coupling become difficult. Engineers respond with segmented traps, microfabricated electrodes, and photonic interconnects that link distant traps via entangled photons. These advances hint at modular architectures where many small ion chains cooperate like neurons in a larger quantum brain. The elegance of trapped ions lies in their clarity. Every quantum operation can be visualized, measured, and tuned. Each ion glows under laser light, allowing experimenters to watch quantum logic literally blink before their eyes. It is precision made visible, a rare blend of beauty and control that brings abstract theory to life. 52. Rydberg atoms link into programmable quantum crystals. Rydberg atoms, with electrons excited to extremely high orbits, carry giant dipole moments that make them exquisitely sensitive to one another. When a group of them sits in an optical lattice, the excitation of one atom can block the excitation of its neighbors, creating effective interactions over micrometer distances. This Rydberg blockade enables the direct construction of entangled states among hundreds of atoms arranged in designer geometries, lines, squares, even triangles that mimic crystal lattices. Laser beams acting as optical tweezers position each atom individually, while pulses of microwave or optical light excite them into Rydberg states for microseconds before returning them to stability. During those fleeting moments, Their mutual repulsion weaves complex many-body states that can simulate magnetism, collective oscillations, and exotic phases of matter. Each atom behaves as both a qubit and a pixel in a quantum simulator, allowing researchers to draw quantum materials from pure light. The ability to control geometry with single-site precision transforms physics into a programmable art. By changing distances and detunings, scientists can emulate spin models, study frustration in triangular lattices, or design novel topological structures. Measurements capture the correlations directly, offering snapshots of entanglement in space. The platform bridges quantum optics and condensed matter, providing a sandbox for exploring phenomena once limited to theory. Rydberg arrays also promise scalable quantum computing. Multi-qubit gates exploiting the blockade effect operate in nanoseconds, and architectures combining optical control with microwave stability could host thousands of qubits. Every experiment resembles a miniature universe whose laws can be rewritten at will, a powerful metaphor for understanding how complexity arises from simple interactions. 53 diamond color centers host photons and spins in one device. Inside a diamond lattice, a missing carbon atom adjacent to a nitrogen impurity forms a nitrogen vacancy center, a defect that traps an electron whose spin can be manipulated and read out with light. These color centers combine the robustness of a solid with the controllability of atomic systems. Their spins retain coherence for milliseconds even at room temperature, while optical transitions allow coupling to single photons for remote entanglement. Microwave pulses flip and entangle spins within the diamond, and emitted photons carry that quantum information through optical fibers to other nodes. Experiments have already linked separate diamonds kilometers apart, proving that entanglement can survive the trip through noisy urban environments. The solid-state host provides mechanical stability, enabling integration with nanophotonic cavities and mechanical resonators that enhance emission rates and connectivity. Such centers serve as hybrid interfaces between matter and light. They can store qubits, act as repeaters for quantum communication, and sense magnetic fields with astonishing precision. Quantum sensors based on NV centers map neural activity and measure single-molecule magnetic fields, bridging physics and biology. The technology scales naturally because diamonds can be fabricated and patented with existing semiconductor methods. Each NV center is a reminder that imperfections can be gifts. A flaw in a crystal becomes a doorway into quantum control, transforming one of the hardest materials on Earth into one of the most delicate instruments ever built. Through these defects, the solid world learns to speak the language of entanglement. 54. Integrated photonics routes entanglement on a fingersnail-sized chip. As optical components shrink from benches to chips, quantum photonics follows. Waveguides etched into silicon or indium phosphide direct single photons through beam splitters, phase shifters, and detectors embedded on the same substrate. These circuits produce, manipulate, and measure entangled states within an area smaller than a coin. What once required a table of mirrors and lenses now fits into the palm of a hand. Integrated photonics offers stability, scalability, and mass manufacturability. Temperature control and electrical tuning adjust phase relationships with micron precision, while on-chip sources generate photon pairs through spontaneous parametric down conversion or four-wave mixing. The same wafer can host detectors that count individual photons, forming complete systems for quantum communication and computation. Miniaturization transforms fragility into reliability. By arranging paths and delays, designers create interferometers for quantum logic gates, boson sampling experiments, and secure key distribution. Arrays of such chips can network together, forming modular quantum processors or quantum simulators with thousands of channels. The approach mirrors the evolution of classical electronics from vacuum tubes to integrated circuits, complexity compacted until it becomes ordinary. Ultimately, integrated photonics could form the backbone of the quantum internet. Entanglement would travel through fiber networks into chips that process and reroute it like packets of light. The story of quantum optics, born in delicate laboratory setups, continues on a new substrate, silicon, the same material that once powered only transistors, but now prepares to host the strangeness of quantum light. 55. Boson sampling hints at tasks that overwhelm classical machines. Boson sampling is a minimalist quantum experiment with no qubits, no feedback, and no algorithms, just photons entering a maze of beam splitters and mirrors. The challenge is to predict the probability distribution of where they exit. Because photons are indistinguishable bosons, their probability amplitudes interfere, creating output patterns whose computation scales exponentially with photon number. Even a few dozen photons render simulation impossible for classical supercomputers. This simplicity makes boson sampling a benchmark for quantum advantage. It demonstrates that even systems without universal gates can perform specific tasks beyond classical reach. Experiments in China and elsewhere have achieved sampling with tens of photons, producing datasets that require astronomical computation to mimic. Verification relies on statistical tests that compare patterns against theoretical approximations, confirming genuine quantum interference. Beyond being a bragging right, boson sampling deepens understanding of complexity. It connects quantum optics to the theory of computational hardness, showing that nature effortlessly computes certain functions humans cannot. The device becomes a physical proof of principle that quantum resources hold more power than classical randomness. Each detected photon represents a solved equation that no silicon circuit could finish in time. The approach also seeds practical innovations. Techniques developed to control, count, and verify many photons feed directly into scalable photonic quantum computers. Boson sampling may not calculate useful answers yet, but it proves the architecture's muscle. In the quiet clicking of detectors, one hears the first bars of computation's next symphony. 56. Measurement-induced transitions reshape quantum phases. In ordinary materials, changing temperature or pressure can shift the system between phases like solid and liquid. In monitored quantum systems, the rate of measurement itself can play the role of a control knob. If a system of qubits evolves under random operations but is observed too frequently, its entanglement structure collapses, producing a transition from a highly entangled volume law phase to a simpler area law phase. Observation becomes the new thermodynamic variable. This phenomenon, measurement-induced transition, emerges in hybrid circuits of unitary evolution and projective measurement. At low measurement rates, entanglement spreads freely, forming complex correlations across the system. At high rates, constant observation pins qubits to definite states, destroying long-range order. Somewhere in between lies a critical point where behavior changes abruptly, a new kind of phase transition governed by information flow rather than energy. Numerical studies and quantum simulator experiments have begun mapping these transitions using arrays of superconducting qubits, trapped ions and photons. Signatures include sudden changes in entropy scaling and fluctuations reminiscent of percolation phenomena. The results blur the line between computation, observation, and physical law, revealing that watching a quantum system can sculpt its state as effectively as any external field. The insight may influence how quantum computers manage errors and measurements. Balancing observation and evolution could maintain useful entanglement while avoiding uncontrolled collapse. In this new frontier, the observer is not an outsider but a tuning knob, proof that attention itself can engineer phases of matter. 57. Entanglement spreads like a wave in many body systems. When a local disturbance strikes a quantum system, information about that event travels outward, not as particles but as entanglement. Correlations between distant regions grow in time, forming a light cone pattern reminiscent of ripples on water. This spreading defines how quickly quantum information can propagate, limited by an effective speed known as the Lieb-Robinson bound. Entanglement, though intangible, behaves as a measurable flow. Experiments with cold atoms and superconducting qubits visualize this process directly. After a sudden change, called a quantum quench, measurements of mutual information reveal how regions become correlated step by step. The front moves at a finite velocity determined by interactions, confirming theoretical predictions that even in non-relativistic systems, information respects causal structure. The wave of correlation is as real as a shock front in air. Understanding this spread helps classify systems as chaotic, integrable, or many-body localized. In chaotic regimes, entanglement grows rapidly until it saturates across the system, while in localized systems, the growth stalls. These patterns control thermalization and memory retention, deciding whether a quantum system forgets or remembers its past. The spread of entanglement becomes the heartbeat of many-body physics. At a deeper level, the visualization of entanglement waves shows that information, not matter, defines dynamics. The universe may consist of moving fronts of correlation, each event broadcasting influence through invisible links. To watch these ripples expand is to watch the very mechanism by which the future becomes informed about the past. 58. Many body localization traps quantum information where it stands. Ordinarily, interacting quantum systems tend toward thermal equilibrium. Information about the initial state disperses through entanglement until it becomes irretrievable. Many body localization defies this rule. In disordered environments, random potentials confine motion so effectively that particles fail to spread and entanglement saturates at modest levels. The system retains a memory of its starting configuration indefinitely, as if time slows to a crawl within the disorder. The phenomenon emerges when interference among countless scattering paths freezes motion, creating localized orbitals that remain stable even in the presence of interactions. Unlike a crystal where order repeats, a localized phase is built from randomness itself, each site a unique trap. Experiments with cold atoms and quasiperiodic lattices, trapped ions and superconducting circuits have directly observed this arrested dynamics, confirming theoretical expectations. Energy exchange halts, and coherence lingers far beyond classical predictions. Such systems offer practical uses as natural quantum memories. Because localized qubits do not share their states easily, they resist decoherence that would otherwise scramble information. Engineers study whether this stubbornness can be harnessed for long-term storage or error-resistant computation. The same mechanisms that impede transport might protect logic. Conceptually, many-body localization reshapes the arrow of time. It shows that isolation and disorder can generate stability rather than chaos, that the universe's march toward equilibrium is not inevitable. In the stillness of trapped information lies an unexpected order, entropy restrained by randomness itself. 59. Quantum scars leave bright patterns inside chaotic systems. In classical chaos, trajectories diverge exponentially and structure dissolves into unpredictability. Yet some quantum systems defy this total mixing by retaining faint echoes of periodic orbits called scars, regions in Hilbert space where probability concentrates along special pathways. These scars cause observables to oscillate for surprisingly long times instead of decaying smoothly, a hint of memory surviving within disorder. Experimental realizations in optical lattices and Rydberg atom chains reveal these persistent revivals. When a system is preferred in a specific initial state, the wave function periodically reconstructs itself, defying expectations of thermalization. The mechanism involves interference among many energy levels that share near-commensurate phases, all tied to hidden symmetries in the underlying model. The result is a recurring pattern, a ghost of classical motion haunting quantum chaos. From a technological perspective, scars suggest new ways to preserve coherence without active correction. By preparing states aligned with scarred subspaces, quantum simulators can maintain oscillations long enough to perform computations or measurements before decoherence sets in. Engineers hope to design Hamiltonians that host robust scars by intention rather than accident. The goal is to sculpt chaos into usefulness. Philosophically, scars blur the boundary between randomness and order. They show that even in the most turbulent quantum seas, certain paths remain privileged, illuminated by ghetto resonance. The coexistence of chaos and memory mirrors the balance between forgetfulness and persistence in nature itself. 60. Entanglement spectra reveal hidden order that ordinary probes miss. Beyond simple measures like entropy, the full distribution of eigenvalues in a reduced density matrix, the entanglement spectrum, contains detailed fingerprints of a system's internal structure. Two phases that look identical under traditional correlation functions can differ in their entanglement spectra, revealing topological distinctions invisible to local observables. The spectrum functions as an X-ray of the wave function's organization, sensitive to symmetries and edge states. First introduced in the study of fractional quantum Hall systems, entanglement spectra now guide classification of topological insulators, superconductors, and spin liquids. A gap or degeneracy pattern in the spectrum often mirrors the energy spectrum of physical edge modes, establishing a deep link between boundary phenomena and internal correlations. Numerical calculations combined with tensor network methods extract these features from simulated systems, translating raw data into conceptual clarity. Experimental access comes through quantum simulators capable of reconstructing reduced density matrices via tomography or randomized measurements. Cold atoms and photonic arrays have begun mapping partial spectra, Confirming theoretical predictions of symmetry-protected degeneracies, each measurement converts an abstract information-theoretic quantity into observable structure, bridging theory and experiment. The insight extends to dynamical situations as well, tracking how the entanglement spectrum evolves after a quench reveals how topological information propagates or decays. This spectral lens transforms entanglement from a single number into a rich landscape, showing that beneath every uniform surface of order lies a detailed terrain of correlations. 61. Topological order stores memory in wholes rather than parts. Topological phases defy the usual pattern of symmetry breaking. Their order resides not in local parameters, but in global features, like winding numbers or ionic excitations. Cutting the system into pieces does not reveal the pattern, only its overall connectivity matters. Because of this, topological order provides us natural protection against local perturbations, making it a cornerstone of fault-tolerant quantum computation. Memory is literally encoded in the holes of the fabric. In such materials, quasi-particles called anyons carry fractional statistics. Exchanging two of them multiplies the wave function by a phase or even a matrix, rather than merely swapping positions. The braiding of these anyons around each other performs quantum gates, with the outcome depending only on the topology of their paths. Errors that do not cross topological boundaries cannot corrupt the information, granting inherent resilience against noise. Experimental signatures appear in fractional quantum Hall devices, superconducting circuits, and engineered spin lattices. Interference patterns confirm the exotic exchange phases, and interferometers measure quasiparticle charges that defy classical fractions. Synthetic lattices built with cold atoms and photonics now simulate these topological phases on demand, turning abstract mathematics into tangible phenomena. The fascination lies in how geometry replaces mechanics. Instead of fragile alignments of atoms, the system's stability comes from the impossibility of continuously deforming one global pattern into another without crossing an energy gap. Topological order teaches that sometimes the surest way to remember is not to record in parts, but to record in the very shape of space. 62. Anyons braid information without touching. In two-dimensional systems, the distinction between bosons and fermions dissolves into a continuum of possibilities. Particles can acquire arbitrary phase factors or even mixed states when exchanged, giving rise to anyons. When anyons trace paths around each other, their braids encode transformations of the quantum state that depend only on topology, not on distance or timing. Computation performed by braiding is therefore inherently fault-tolerant. Noise that does not change the braid pattern cannot alter the result. The most celebrated candidates for anyonic behavior appear in fractional quantum Hall systems and in certain superconductors hosting Majorana zero modes. Interferometry and tunneling experiments search for signatures of non-abelian statistics, where exchanging particles acts like a rotation in a multidimensional state space, rather than a simple phase shift. Detecting these effects is demanding because the systems must remain extraordinarily clean and cold, but evidence continues to accumulate. Topological quantum computing aims to exploit these braids as logical gates. Moving quasiparticles along specific trajectories would implement computations protected from local errors. In practice, implementing and reading out such braids require exquisite control of nanostructures and magnetic fields, pushing experimental capabilities to their limits. Each successful manipulation is both an engineering feat and a small dance of mathematics made real. Anyons embody the idea that interaction need not mean contact. Their choreography in the plane computes through pure geometry, turning motion into logic. In their swirling exchanges lies a glimpse of how the universe might perform calculation in silence, by merely letting shapes intertwine. 63. Quantum batteries promise charging through collective effects. A classical battery charges as individual particles absorb energy independently. A quantum battery could charge faster by exploiting collective entanglement among its components, allowing energy to be distributed coherently. Theoretical studies show that n quantum cells can achieve a speed-up proportional to n rather than its square root, a dramatic advantage known as quantum supercharging. Entanglement thus becomes not only a means of communication but a catalyst for power. Model systems include ensembles of two-level atoms coupled to a common field, where simultaneous excitation creates cooperative dynamics reminiscent of superradiance. Experiments with superconducting qubits and cavity photons have begun exploring these regimes, measuring enhanced charging rates and collective discharges. The effect depends on maintaining coherence throughout the process. Any decoherence reduces the gain, underscoring the delicate balance between order and usefulness. Beyond speed, quantum batteries offer precision control of energy flow. By engineering specific Hamiltonians, one can design protocols that transfer energy without waste, reaching bounds set by quantum thermodynamics. Research also investigates passivation, ensuring stored energy cannot leak without external drive, a property absent in ordinary devices. Energy itself becomes quantized inventory under algorithmic control. Although still conceptual, quantum batteries hint at a future where microscopic devices harvest and release energy in quantized bursts, synchronized by entanglement. The dream combines elegance and efficiency, power delivered not by chaos but by coherence, as if the universe learned to charge itself through Yamini. 64 quantum heat engines use coherence as a working fuel. In classical thermodynamics, engines convert heat into work by cyclic processes between reservoirs. Quantum heat engines operate on the same principle but exploit discrete energy levels and coherence between them. Coherent superpositions can enhance efficiency beyond classical limits without violating the second law, because they redefine what equilibrium means at microscopic scales. The quantum version of a piston may be a two-level system oscillating between states rather than a moving cylinder. Different architectures, Otto, Carnot, or Stirling cycles, have been implemented using trapped ions, superconducting qubits, and single spins in solids. These setups measure work and heat at the level of individual quanta, observing fluctuations that would be invisible in macroscopic engines. Some demonstrate quantum supremacy in thermodynamics, faster work extraction, reduced dissipation, or novel modes like population inversion used as fuels. Coherence plays the role of a catalyst. When phase relationships among energy levels are preserved, transitions interfere constructively, producing more work for the same input energy. Conversely, dephasing converts the machine back to classical behavior. Understanding how to maintain and harness coherence may redefine efficiency for nano-engines, powering future sensors and processors. Quantum heat engines close the circle between energy and information. They show that work is not only a mechanical concept but also an informational one, order extracted from randomness. The next industrial revolution may run not on steam or silicon, but on phase and entanglement. 65. Entangled sensors map fields with needle-sharp sensitivity. Sensing weak signals often depends on averaging over many independent probes to reduce noise. Entanglement changes the game. Correlated probes can surpass the classical shot noise limit, achieving precision that scales inversely with particle number rather than its square root. This quantum advantage, known as Heisenberg scaling, allows detectors of magnetic, electric, or gravitational fields to reach sensitivities unattainable by classical means. Experiments with atomic ensembles, interferometers, and superconducting qubits have already demonstrated sub-shot noise measurements using squeezed or entangled states. LIGO's Gravitational Wave Observatory injects squeezed light to extend its reach, and atomic clocks use spin-squeezed atoms to track time more accurately. Each success turns quantum correlations into tangible performance. The challenge lies in balancing gain and fragility. Entangled states amplify signal, but also amplify susceptibility to decoherence. Techniques such as adaptive measurement, error correction, and differential setups mitigate these vulnerabilities. The art of quantum sensing is to keep the collective whisper coherent while the world roars with noise. Ultimately, entangled sensors blur the line between observation and participation. They sense by being part of the phenomenon they measure, their internal correlations resonating with external fields. Precision becomes a dialogue rather than a one-way reading, proving once again that connection itself is the finest instrument. 66. Ghost imaging builds pictures with light that never meets the object. In ghost imaging, an image of an object is reconstructed using photons that never touched it. The method begins with correlated photon pairs. One photon, the signal, interacts with the object while its partner, the idler, travels a separate path to a detector with spatial resolution. The object arm uses a simple bucket detector that records no spatial details, only total intensity. Yet when coincidence counts between the two detectors are analysed, a full image emerges. the pattern of correlations carries the picture invisibly until the data are matched. Originally, ghost imaging was achieved using entangled photon pairs from spontaneous parametric downconversion, but later experiments showed that classical correlations in thermal light can mimic the effect. Still, the quantum version provides higher contrast and works at lower light levels, demonstrating how entanglement can encode spatial information across distance. The image is a manifestation of shared quantum statistics rather than local illumination. Applications extend to imaging through turbulence or opaque materials, where direct paths scatter light beyond recognition. Because the reference beam never interacts with the obstacle, it preserves spatial coherence lost in the test arm. Combining the two streams restores visibility of the hidden scene. Quantum ghost imaging thus turns correlation into a lens capable of seeing through chaos. The concept challenges intuition about what it means to see. Vision becomes an act of inference rather than contact. The object is reconstructed not from its own reflected photons, but from the whispers of their twins elsewhere. In a sense, the universe photographs itself through its entangled reflections. 67 Quantum illumination finds targets in glare and noise. Quantum illumination exploits entanglement to detect faint objects hidden in bright or noisy environments. A source produces entangled photon pairs. One photon probes the target region while its partner remains in the lab as a reference. Even after environmental noise destroys the entanglement, residual correlations between returning and retained photons can still reveal the presence of a weakly reflecting object with a higher signal-to-noise ratio than any classical scheme. The advantage survives decoherence, a remarkable resilience for quantum effects. The principle was first demonstrated in microwave and optical regimes, showing detection improvements of several decibels over classical radar-like systems. The method does not rely on fragile coherence but on subtle statistical relationships encoded at emission. By comparing the returned signal with the stored reference, receivers can discriminate target echoes from overwhelming background clutter. It is quantum metrology adapted to the battlefield of noise. Potential applications include low-power radar, biomedical imaging, and remote sensing where stealth or safety demands minimal illumination. Because quantum illumination uses fewer photons for the same detection probability, it can image delicate samples without damage and detect objects without revealing its presence. Researchers continue to explore practical hardware combining optical parametric amplifiers and superconducting detectors for real-world performance. Quantum illumination demonstrates that quantum advantages need not vanish with entanglement's fragility. Even broken, the pattern it leaves behind enhances perception, much as a shattered mirror can still reflect. The universe seems to remember its correlations even when we think we have lost them. 68. Quantum radar tries to see through clutter with correlations. Building on the ideas of quantum illumination, quantum radar seeks to use entangled microwave photons to detect and characterize distant targets amid thermal noise and interference. Classical radar transmits coherent waves and measures echoes, but its sensitivity diminishes rapidly with distance and clutter. Quantum radar, by contrast, would transmit one half of an entangled pair while keeping the other as a reference. Even after decoherence, subtle correlations could make detection more robust and precise. Developing such systems at microwave frequencies is technically demanding. Generating entangled microwave photons requires superconducting parametric amplifiers operating at millikelvin temperatures, while preserving correlation through the atmosphere challenges current materials. Nonetheless, laboratory prototypes have demonstrated measurable quantum correlations in returned signals under controlled conditions, suggesting that scalable versions may one day outperform their classical counterparts. Beyond detection, quantum radar could measure velocity, range, and even the material properties of a target with unprecedented sensitivity. Its information-rich echoes would contain signatures of quantum interference, allowing identification of objects hidden behind clutter or camouflage. In the future, networks of quantum radars could coordinate through shared entanglement, mapping the environment with near-theoretical precision. The vision extends radar from waves to relationships. Instead of illuminating objects with energy alone, it illuminates them with knowledge, patterns of correlation that persist even through noise. Seeing becomes an act of decoding how the world responds to being entangled. 69. Photosynthesis hints at coherence in warm biology. For decades, quantum effects were assumed irrelevant in living systems because thermal noise should destroy coherence instantly. Yet ultra-fast spectroscopy of photosynthetic complexes reveals oscillations in energy transfer pathways lasting hundreds of femtoseconds, long enough to influence efficiency. These quantum beats suggest that excitonic states within pigment protein complexes remain coherent, allowing energy to explore multiple routes simultaneously before settling into the reaction center. Nature, it seems, may compute optimal paths with quantum algorithms. The coherence arises from the delicate balance between electronic coupling and vibrational motion of the protein scaffold. Environmental fluctuations, instead of destroying quantum behavior, may even stabilize it through a process called environment-assisted quantum transport. The system rides the edge between order and chaos, where noise helps steer energy rather than dissipate it. Efficiency close to 100% emerges, not despite disorder, but because of it. Experiments on light harvesting complexes in algae, bacteria, and plants continue to refine this picture. The persistence of coherence at physiological temperatures challenges preconceptions about the limits of quantum mechanics. If life indeed exploits such effects, evolution may have tuned molecular architectures to harness the benefits of quantum dynamics naturally. Photosynthesis thus stands as a bridge between physics and biology, showing that quantum processes need not vanish in warmth and water. The green color of leaves hides a computation running silently in sunlight, proving that life itself may have been the first quantum engineer. 70. Radical pairs in birds may preserve entanglement during flight. Migratory birds navigate using Earth's magnetic field, a feat still not fully explained. One compelling hypothesis invokes quantum entanglement inside pairs of molecules in their eyes. When light excites certain proteins called cryptochromes, it creates radical pairs, molecules with unpaired electrons whose spins are initially entangled. The weak geomagnetic field alters the interconversion between singlet and triplet spin states, affecting subsequent chemical reactions and thus influencing the bird's sense of direction. Evidence for this quantum compass grows yearly. Experiments show that magnetic fields as small as Earth's can affect chemical reaction yields in cryptochrome-based systems, and that radiofrequency noise disrupts orientation in some species. The implication is that delicate spin coherence survives for microseconds within warm biological tissue, long enough to mediate sensory perception. If true, birds perceive magnetic lines through quantum chemistry. The physics behind this mechanism intertwines spin dynamics, molecular motion, and reaction kinetics. The competing processes of decoherence and recombination determine how long entanglement persists. Laboratory analogues with artificial molecules confirm that such coherence can endure far longer than expected, lending credibility to the biological hypothesis. The avian compass may be evolution's version of a quantum sensor, honed by migration across millennia. In poetic terms, each bird may carry an invisible quantum experiment within its eyes, measuring the planet's field with precision no human instrument can yet match. Their flight paths could be written in the language of spin and light, proof that quantum phenomena have already taken to the skies. 71. Smell theories flirt with tunneling and molecular spectra. The sense of smell has long been modelled as a lock and key mechanism, where receptors recognise molecular shapes. Yet some researchers propose that olfaction also involves quantum processes, such as inelastic electron tunneling. According to this theory, odorant molecules enable electrons to hop between receptor sites if their vibrational frequencies match the energy gap, a resonance that depends on molecular composition rather than shape alone. The brain would thus detect smell through spectroscopy conducted at body temperature. Evidence remains controversial but intriguing. Experiments comparing molecules with identical shapes but different isotopic compositions show perceptible differences in odor, suggesting sensitivity to vibrational spectra. Quantum tunneling would explain this discrimination naturally, as isotopes alter vibrational energies without changing geometry. Receptor proteins may act as molecular spectrometers exploiting resonance-assisted charge transfer. Testing the hypothesis involves measuring electron currents through single receptors and modelling how biological noise affects tunneling rates. If confirmed, the olfactory system would represent a unique biological quantum detector operating amid constant thermal agitation. It would prove that quantum coherence can coexist with biochemical complexity, not as a rare anomaly, but as an everyday sense. Even if the full picture remains unsettled, the idea invites a broader view of perception. Smell could be the first sense where humans unconsciously perform quantum spectroscopy, turning the invisible motion of electrons into memories of roses, smoke, and rain. The universe is like a sleep woven with invisible bonds. We are in that sleep, like atoms that feel each other without touching. Maybe even our thoughts vibrate at the same time as particles in those distant stars. The flow of time, the chains of cause and effect, even the idea of who we are, all could be echoes of this invisible weave. Now close your eyes and think about this. If everything is connected, you have never slept alone. If you enjoyed this journey, don't forget to like the video, comment and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realise. Science is the most powerful way to understand this strangeness.